Welcome to exercise 6 of chapter 9. Here we will explore the norms of orthogonal matrices. There's quite some interesting properties of orthogonal matrices with regards to their norms, their eigendecomposition, and singular values and singular vectors and so on. Now, there's a lot of text for this exercise, but you don't actually need so much code to solve this exercise. And that's because, I've wanted to take this opportunity to just teach you some interesting properties of orthogonal matrices. Okay, some of which is that their singular values and their eigenvalues are all 1. Now, I haven't yet in this book introduced you to singular value decomposition and eigendecomposition. So you will learn more about that and interpreting these values later in the book. But an implication is that the induced 2 norm of any orthogonal matrix is 1, and the Frobenius norm of any orthogonal matrix is M, where M is the size of the matrix. So, M columns or M rows of an orthogonal matrix, and that is the Frobenius norm. Okay, so then I talk a little bit about why this is, although I have to admit, to really appreciate why these properties are the way they are, you need to know about the singular value decomposition, which you'll learn about later on in the course. Okay, so what you want to do here in this exercise is create an M by M orthogonal matrix, compute its 2 norm, and compute its Frobenius norm. And then with the Frobenius norm, you want to divide by the square root of M, so the number of columns, and you want to just confirm that both of these scaled norms are equal to 1. So let's start with the code for that. There's more to this exercise, which is also going to teach you another interesting property of Q matrices. There's even a proof down here, but let's just stick to what I have discussed so far in the code, and then I'll come back to the book here. So here I create some random orthogonal matrix through QR decomposition of a random numbers matrix. Now, again, this is like what I have said a few times in some of the previous exercises. In this case, we don't really care about the QR decomposition per se. We just want an orthogonal matrix. And so there are a few different ways to create a random orthogonal matrix. And right now, at this point in the book, the only way that you know how to create a random orthogonal matrix is by taking Q from the QR decomposition of a random numbers matrix. You can also get Q matrices from eigendecomposition or from singular value decomposition, and you'll learn about those later in the book. Okay, so we just want this matrix Q. Here we compute the induced 2 norm. That's through numpy.linalg.norm. And if you provide a second input of 2, then that is the signal to numpy that it should return the induced 2 norm. Okay, and then we also take the Frobenius norm here as the all the individual elements of the matrix squared, summed, and then the square root of that. So this is the Frobenius norm of this Q matrix. And then here I'm dividing by n, where n is the number of columns. And then as I wrote in the text, both of these should be equal to 1. Here, this is hilarious. This is 1.00002. Just one little lonely 2 at the end. Let's see what happens if I run this again. Okay, now here we get 4 and 2. Of course, these are tiny, tiny, tiny numbers. These are just little computer rounding errors. You don't need to worry about them. If you expect a theoretical result to be 1 and you get a number like this, that is 1 plus some rounding error. What does the induced 2 norm even mean? Well, there's a few different interpretations of the induced norm. One of the interpretations of an induced norm is the maximum amount of stretching that a matrix can apply to a vector. So if you think about multiplying a matrix by a vector, so matrix vector multiplication, you know that the matrix can have 2 impacts on the vector. It can rotate the vector and it can scale the vector. So the resulting vector can be shorter or it can be longer than the original vector. And in particular, imagine some vector v, and then we have the vector qv, where q is an orthogonal matrix. So Q is going to rotate v, and the question is, can Q make V longer or shorter? Now, the induced 2 norm tells us the longest that factor could ever be. So for example, if the 2 norm equals, let's say 5, then that means that for this Q, if this had a 2 norm of an induced 2 norm of 5, not for this Q matrix, but for some other random matrix, if a matrix had an induced 2 norm of 5, then it would mean that the largest it could possibly scale any given vector would be 5. Now, that doesn't mean that every single vector will be stretched by a factor of 5. Obviously, if V is the zeros matrix, then it's not going to stretch it at all. But the largest it could possibly stretch would be a factor of 5. Okay, so if the Q matrix, if an orthogonal matrix has an induced 2 norm of 1, that means that the maximum it can possibly scale a vector is a factor of 1, which means it's not scaling at all. So it can rotate, but it cannot scale. It can't make the resulting vector be shorter or longer. Okay, so that is what we are going to do in this part of the exercise. Create some random column vector V, and of course it has to be m-dimensional because we are going to compute QV. So compute the norm of V and QV, and those norms should equal each other. Again, the norms are not going to be 1. The ratio of the norm between QV and V is going to be 1. So that's what I do here. I create a random numbers matrix, and then I compute the norm of that vector. I said matrix, but I meant vector. The norm of that vector, and then the norm of Q times that vector, and then I print them out. Again, we don't expect these to be 1 because the norm is going to be whatever this happens to be. The important point is that because Q is an orthogonal matrix, then it has an induced 2 norm of 1, and that means the amount of stretching is going to be a factor of 1. So this is not going to change the magnitude of this vector. It'll rotate it, but it won't change the magnitude or the distance away from the origin. Finally, we get to the last part of this exercise, which is for you to work through a proof of that empirical demonstration. So again, the empirical demonstration that the norm of V and the norm of QV are always going to be exactly the same as long as Q is an orthogonal matrix. Okay, so I'm going to now explain the proof, which is also written out in this paragraph. It's a really simple proof. I hope you managed to work through it on your own. Basically, the idea is that we compute the norm of V, which is V transpose times V, and then the norm of QV. Now, the norm of QV is just the dot product of QV with itself. So that's QV transpose QV. This here we use the live evil rule. So we can write out this expression as V transpose Q transpose times QV. And now the trick, which isn't really a trick, but it's a little bit of insight, is to, instead of associating these two items together and these two items together, you associate the two Q's in the middle together. Now we know that Q transpose Q is the identity matrix. So that means that the magnitude of QV is the same thing as V transpose times V, which is the magnitude of V. So that is the proof that works only because Q transpose Q is the identity matrix. So this special property holds only for the case where the matrix times its transpose is the identity matrix, which is obviously the case for any orthogonal matrix. So the conclusion from that proof and this whole exercise is that orthogonal matrices can rotate a vector. They can change the direction, but they cannot scale. They cannot make a vector shorter or longer. That may sound sort of academic and esoteric and sort of pointlessly detailed mathematically, but it turns out that that property is really important. This is an important property for principal components analysis, for example, and lots of other advanced applications in multivariate analyses and machine learning techniques.